Hello everyone, hope you all are doing great. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and I've been a computer programmer over a long time. So yeah, this playlist, as you know, it's about Leetcode Biweekly Contest 123, and this video is specifically focused on problem number 3, that is maximum good subarray sum. So as I had mentioned earlier, the strategy you should use is look at the approach that I'm using to solve this, how I'm reaching that approach, and then pause the video at intervals and think yourself how you'll solve the video instead, and then compare against how I am solving it. That's the best way to actually benefit from these videos. So yeah, let's get started. So the question says this: you're given an array and a positive integer k, and a subarray is called good if the absolute difference between its first and last element is exactly k. So whether a subarray is good or not depends on its first and last elements. If the difference is k, absolute difference, then it is a good subarray. This is the formal interpretation. Now return the maximum sum of a good subarray of nums. So out of all the good subarrays, you have to find out the maximum sum. And if there are no good subarrays, then you have to return 0. That is the last condition. So that is the first part of the problem, that you have to understand the problem from its lines. The second part of solving every problem should be the test cases. So come to the test cases. In the interest of time, I'll take up one test case to explain how it goes. I'll take the second test case. It goes somewhat like this. -1, 3, 2, 4, 5 and k equals to 3. 3, 2, 4, 5 and k equals to 3. So basically k is the difference between the first and the last element. So if I see the difference between -1 and 2, the absolute difference between -1 and 2 is equal to 3, so this is a valid, this is a good pair. Then also I can say, okay, from 3 to 5 no, from 2 to 5 yes, from 2 to 5 it is a valid pair, from 3 to nothing, so this is another valid pair. Why? Because 5 minus 2 is equal to 3. So what is going to be our answer now? These are two such things. So one subarray is -1, 3, 2, another subarray is 2, 4, 5. So if I look at the first subarray, -1, 3, 2, then the summation of the elements is -1 plus 3 plus 2, that is 4. And if I look at this particular subarray, it will be 6 plus 5, 11. So basically, which one has the maximum sum is the last one, that is 11. I need the sum, so my answer has to be 11. If I look there, the answer should be yes, the answer is 11. So the answer is 11. Now, the next thing that I should look at, I can think about an approach quickly, but often the technique that we computer programmers use is look at the constraints. That will give you an idea of what time complexity is allowed. So this one tells you that if nums.length is basically n, let's say that is n, then n squared is not possible. 10 to the power 5 is too large for n square time complexity to pass. So then we have to settle down for n log n, maximum n root n, that too the constants have to be lesser. But n log n and then are probably the things that we should try. Okay, so now how should we try? So let us try to understand. According to what the problem says, that last element minus first element, the last element minus first element is equal to k. So basically, what can I say? When I come to an element, let's say I've come to the last element, L. What can I say? The element at index L, let's say it is AL. I can say that, okay, I can form a good subarray if there is an element before it which is k lesser than this. I missed this absolute sign. So yes, absolute difference is equal to k, which means that if I get some element AL minus k, that is going to satisfy, or if I get an element AL plus k, either of them before myself, then I can satisfy. For example, let's say k is equal to something like let's say 3, and I have an element 5, something like 1 over here, let's say something like 2, maybe -1 and 8 and 1, maybe something like this. So what do we see here? The difference, so if I look at this element, if this is my index L, so this particular element, if it wants to form a good subarray, if it has to be the last element of a good subarray, what can be my first element? I can see that this guy, 2 can be my first element because 5 minus 2 is equal to 3, which is equal to k is equal to 3. And it can also form a good subarray with 8. Why? Because 5 minus 8 is equal to 3 minus 3, and the absolute of it is basically 3, the magnitude is 3. So what does it tell me? That 5 has the capability to pair with both 2 and 8. So this gives me the question, this brings up in the question, which one is better for me? Yes, we have already discussed it. The better one is basically whichever subarray gives me a bigger sum. So 215 gives me a sum of 7 plus 1, 8, and the other one 8 minus 1, 215 will give me a summation of 7 plus 8, that is 50. Yeah. So this is the primary understanding of the problem. Now the thing is, using this last element, I know how to pick out my first elements. I can't go pairwise. I can't go for every ij. That is what would take it to n square. So I have to settle for less than n square. So this is one observation. There is one condition given, and from that condition I get a straightforward thing, that okay, if I know the last element, I know my first elements. They have two possibilities. These are the two possibilities. With these two possibilities, whatever is the biggest sum, that is what I should track. Now I have to do this for every last element. That is a different thing. But how to find this summation? Once you have found out that okay, this particular thing is at some index, let's say instead of r, I may call it something like k, or let's say s. So from s to l, how do I get the sum of elements? Sum of elements. Brute force would be that add all the elements, as plus up to al minus 1 plus al. Add all the elements. But we know that this can easily go up to big O n. And for every summation calculation, we can't afford big O n. So we'll definitely try to optimize it. We already know that this is the sum of a continuous subarray. And whenever we are talking about a continuous subarray, the summation or such properties which are additive or similar, we can basically use our prefix sum, those kind of techniques. So you can easily say, hey, this is nothing but your prefix sum of L minus prefix sum of S minus 1. So it is only the prefix sum that I need. So whenever I come to an L, I can say, hey, using this L, tell me what is the element over there. From this, tell me what should be the element of the source, the start element, and I can keep some data structure to tell me where that start element is. So I can keep some data structure to tell me the position of that start element. There are two possible start elements. So I can take something like this, start element 1, which is minus k, and start element 2, which is plus k. And then I can apply some data structure to basically give me a second position. Now, what if you have such cases where you have multiple 8s over here? There are other elements as well about 8s. Can we say that this 5 will find every 8 interesting? Which 8 is interesting to us? Which 8 should this 5 look for? We already know that. It's not the length of the subarray. If all the elements are positive, we can say, but all the elements are not positive. The elements can be negative as well. So it's not the length of the subarray. It's basically the sum. Whichever one gives me the maximum sum of subarray. And what is the maximum sum of subarray? We have to maximize this. So if for different start elements, this particular condition is preserved, this minus plus k, this k condition is preserved for different start elements, how will I choose the best start element for myself? Whichever gives me the maximum sum. So if this sum is maximum, I'll take this. If this sum is maximum, I'll take this. And how can I maximize the sum? By maximizing this expression. Prefix sum of L is already fixed. So I can say that this one I have to reduce as much as I can. Once I've fixed the last element, prefix sum up to last element is fixed. So I can say, okay, whichever 8's prefix sum will be least, that will be my objective. Using that, I can have the maximum possible sum from 8 to 5. Make sense? So yeah, in order to maximize this, my approach would be to minimize this particular thing. And how to minimize, how to store so many elements and minimize? No, you don't require all the prefix sums. Just store whichever is the least. So when you're remembering, whenever you're remembering that for 5, whenever you're remembering 8, 3, for 8, 3, etc., just remember, okay, where did 8 occur with the minimum prefix sum? 5 will readily catch that. 5 will say, hey, I need 2 and 8, 5 minus 2 and 5 minus 3 and 5 plus 3. So 5 plus 3, 8 will take me there to a data structure, and I'll request, hey, with 8, if you have some start element 8, can you tell me what is the minimum prefix sum before that? Before that element, what is the minimum prefix sum? P of s minus 1. So before that, what is the minimum sum? If I get the minimum there, I can subtract and get the maximum possible subarray sum. So yeah, that's all that the algorithm is about. Let's take a look at my code and see how I've translated the entire thing. This is my coding implementation. I've used a hash map. Why did you use a hash map? In order to tell me that for every element that I'm searching, what is that minimum prefix sum? So it's something like a key value pair. For every sum, I'm asking, hey, for 8, what is the minimum prefix sum you have? For 2, what is the minimum prefix sum you have? And so on. So for these 2 elements, if I have only these 2 operations, hash map makes it very easy to fetch that particular prefix sum and help me with the rest of my calculations. So that's where it goes. For every element, I'll basically ask that, hey, if map contains num psi minus k, then that is the element minus k. If it contains, you need to check whether it is there or not. If it is there, then definitely you can just subtract it. So sum plus num psi. This is how I'm basically calculating sum. So sum is initially 0, and I'm adding the current element to the sum at the end. So over here I'm saying, okay, sum up to me is basically sum plus num psi. And what is the summation just before this guy, before this num psi minus k? I'm storing that in map. So map will basically store what is my prefix sum, minimum possible prefix sum before that. Now let us see nums I plus k. Maps.gets, okay, yeah, if sum is less than, right. I'm also checking for this num psi plus k, the other one, exactly in the same way. So I'm basically saying, hey, if the difference, what is this difference? This is a subarray sum. Difference between the prefix sum is a subarray sum. So I'm calculating this for both plus and minus k, and I'm taking maximum on the answer. The answer I've initialized with long.minimum value. Don't start with 0 because though you have to return 0 in case of invalid, but your answer may be something like minus 2, minus 3 or something like that. See, you have an answer of minus 6. So definitely in such case you should avoid starting with 0, because since you are finding the minimum answer, right? Maximum, so minus 6 will not be taken as the maximum when you have 0 as the default. So you should start with minimum value so that those minus values etc. are considered. And then what am I doing next? I'm basically coming to this particular line. Map contains that particular num psi or not. That is, this is my current element I. So I'm storing the prefix sum before I for the next iterations, so that my next iterations can get this value. This is where I'm updating the map. So I'm asking, hey, do you have num psi? And if you have num psi, is the current sum going to be better? If the current sum is lesser, then it is better. I'm searching for the minimum prefix sum to be stored. So this is better. And if it is not there, then also you should add it. So either it is not there, or whatever is present, that is greater than what I currently have. So in that case, I'll store what I currently have for this particular element. So I'm storing the key as the element because it's the element minus k or element plus k, that value that I'm going to look up the hash map for. That's it. So the hash map is storing what is there before I. Before I go to I plus 1, I'm going to basically add num psi to sum. So that when I go to I plus 1, sum will basically have the sum of elements up to I. So in this way, it is totally connected end to end. There is no issue anywhere, and this is what you need to be careful about. Every edge case gets covered when you're carefully coding, when you're considering every possibility of edge case of minus plus. By the way, so and at the end, I'm using a ternary operation. You can use an if else also. If it is equal to long dot min value, it is going to return 0 or it is going to return answer. That's it. So what is the time complexity? The time complexity is of this approach. This is n iterations, and every iteration is basically a map lookup and a map update, or 2 map lookups, or maybe 2-3 map lookups and a map update. Now the question is, what is the time complexity of this map lookup? If you use a tree map kind of structure, it is log n. If you use a normal hash map, it is usually big O1. Here also it will be big O1, but theoretically it can go up to big O(n) in a very, very worst case. But that is a very, if you read the details of hash map, you'll get something from the internal workings. You can ignore that for a while. You can basically treat it. In general, it is big O1. From collisions, it is the possibility of big O(n) sometimes arises, but you can leave that while you are coding in general. So it is big O1 for the moment as we are taking, and any iteration, so it is big O(n) time complexity and big O(n) space complexity, because at the maximum we are storing n elements in the hash map. Yeah, so that's it. Before we close on the video, the last point. Do you notice any loophole in the video? Pause the video and try to see. Is there any loophole? Do you think a case where it will not work? So I have not tried it, but while explaining it basically struck me. When we are doing this minus k plus k, since we are updating the map after this, we are not going to get the current element in the map. So current element I'm not going to get in the map. So basically, if I say for this 6, I'm not going to get 6 in the map while I'm checking for 6. And that is only important when k is equal to 0. If k is equal to 0, then current element will basically find solace with the current element only. I will say this is my subarray, 6. 6 to 6, this is my subarray. And that is the maximum sum over here. Why it didn't pay me over here? Because it is given that k is greater than or equal to 1. So according to this constraint, yes, this solution is totally correct. This is an accepted solution. But in case if you are in an interview, either you need to specify, hey, I'm considering this particular constraint, or you need to be really very sharp at that point of time, very relaxed, and you have to internalize the entire thing to come up with that particular edge case. That, hey, when k is equal to 0, this is 1. Okay. Thank you. Hope you understood the video. Thanks for joining. Let me know if you have any other approaches that seem better to you. But this is how these problems can be solved. This is how, with basic concepts clearly there in your mind, you can solve many problems for your interview preparation. And so many. Okay, see you all. And before I finish, please share your likes, subscribe, comments. They are highly helpful in boosting me up for all the next videos. See you all in my next videos. Thank you.